Field walking with drones. This is a work review of work in progress on a new project about an old subject. Field walking, also known as pedestrian survey, is a time-honored archaeological tradition. In field walking, a team of people are assembled from whoever is available. They stand beside each other in a line on one end of a field and they walk together towards the other end of the field, looking for artifacts on the ground as they go. If they see one, they plant a little flag there and continue across the field. It may seem silly at first. Assemble a group of people, whoever you can find, describe what to look for, hand them little flags and notebooks, and turn them loose to march across the field together. But this is what is done ever since archaeologists began to invent systematic ways to examine their sites. All over the world, archaeologists are quite literally outstanding in their field searching for antiquities. Yet for all its imperfections, this practice helps us understand the living patterns of ancient people and the places where they lived. Organizing a field walk is never easy. It means gathering a group of people, sometimes seasoned archaeologists, sometimes their assistants or students, sometimes volunteers or curious locals, and asking them to form a line and carefully examine the ground in front of them. These teams are eclectic, with a wide range of experience and skill. Some know exactly what to look for, and others are still learning. Some have sharp eyes and keen attention, while others may struggle with the terrain. It's not a perfect process, and these kinds of challenges, the uneven skill levels, the physical limitations of the walkers, the sheer difficulty of scanning a field by foot in the hot sun, can lead to gaps in the survey. Important details can be missed, and misunderstandings of the site can arise, and that's why we believe this age-old practice of walking the field can be powerfully augmented through drone imagery, capturing high-resolution visuals of every inch of the terrain. This will add precision and consistency to a process that has, until now, depended solely on human observation. So here I describe 4 general types of drone surveying that are valuable for archaeological research. The first is orthomosaic survey. In this method, the drone flies in a programmed grid pattern, shooting hundreds of photos straight down, what we call a nadir trajectory. These images are stitched together in software to form one massive high-resolution image of the entire area. Second type is a surface model. It's also known as photogrammetry. Like the orthomosaic, it involves shooting hundreds of photos too, but this time from an angle. And that angled perspective allows the computer to reconstruct a 3D model of the area, giving us a sense of elevation, shape, and texture. The third type is video imaging. We're all familiar with the stunning drone footage from travel videos, but in archaeology, video can also be a powerful tool for site analysis, especially when capturing movement, spatial relationships, or environmental context. The fourth type, and this is the one we're focused on, is the aerial survey. It's similar to an orthomosaic in that it covers the entire area systematically, but it's done at very low altitude. The goal here is not just visual documentation, but to enable AI analysis. By flying low and capturing high-detail images, we give the AI model the best possible chance to detect and identify small objects, like pottery sherds. When we talk about a complete aerial survey, it's important to clarify what we mean. This isn't an aerial survey as in a survey from the air. It's an aerial survey meaning a comprehensive survey of a defined area. The goal is to create a high-quality visual record of every single spot within the target zone. This allows for detailed analysis after the fact using non-intrusive methods to document the entire site. It also ensures that every object is tied to precise geospatial coordinates so that we can detect, locate, and analyze those objects. With the help of AI, we can generate a tabular inventory of what's present, the type of object, its visual character, size, and exact physical location, supporting research into population estimates, settlement patterns, and land use models. By photographing every square inch of a field, we create a detailed, accurate, non-destructive record of the site, one that complements and enhances traditional field walking. So that's the introduction to the kind of work we're doing. Now I want to tell you about the specific project we're working on right now. We are working in the fields west of the Maya archaeological site of Lamanai, close to Indian Church Village, about 50 kilometers northwest of Belize City. You can see the 2 mounds I will describe, Platform 1 and Platform 2, as yellow and blue stars in the map inset, and you can see them again very small at the top of the map where they appear as yellow and blue dots. You can see the New River Lagoon under the letters W and D in the words Orange Walk District on the map. The 2 mounds are about 1 kilometer apart. The tropical forests west of Lamani have concealed Maya ruins for over thousands of years. In this image, you barely see the outline of a large ancient structure. Covered in thick growth, the plants are so dense it's almost invisible. No one knows exactly what it is or what's hidden there, and the pottery sherds and other artifacts which could tell us so much about the people who lived there remain buried in the underbrush. Forests are full of ruins like this, waiting to be examined and understood. Then comes the Mennonite farmer on his tractor, clearing the forest for agriculture. With bulldozers and chains, the land is leveled for planting. Ironically, this destruction gives us our only brief glimpse into the ancient world. As the forest is cleared, ruins are exposed, just for a few days before crops are planted and the past is hidden once again. In that short window, we can see the outlines of platforms smeared across the landscape amid scatters of pottery sherds, fragments from the homes of Maya families long ago. During these fleeting days, the farmers generously allow archaeologists to walk their fields, documenting what remains, trying to piece together the story of the place. These fields, filled with the remnants of vanished communities, present enormous challenges. Vast open areas, many square kilometers in size, reveal patterns of domestic settlements strewn with thousands of distinctive Maya pottery sherds, mixed in the crushed limestone debris. Could AI detect those distinctive red pottery sherds scattered across the Mennonite fields of Belize? Our goal is to develop methods, tools, and techniques for detecting Maya pottery sherds using drone imagery and AI deep learning. We began this work last summer when I arrived in Belize at the field camp where Dr. McClellan, located in Indian Church Village at the archaeological site of Lamani, was working with his drone. Here I will outline our key steps in our process, steps that are broadly applicable to any project aiming to build an AI object detection model from field data. Step 1 was to mark confirmed pottery sherds on the site with little red survey flags. This was done to provide confirmed ground truth samples of the sherds in the drone images. After tagging the artifacts on the target areas, the next step was to fly the drone at very low altitude and shoot photographs of the target area. Back at the studio, we pre-processed the drone footage, imported it into GIS software, and manually drew outlines around hundreds of individual pottery sherds. Now we're using those sherd outlines to create training samples to feed to the AI deep learning model so it will learn what Maya pottery sherds look like. And our last step is to run the model on previously unseen terrain to run validation tests on it to confirm and measure its effectiveness. So that's the overview of our planned workflow. Now let me show you how we're putting this into practice. Step 1 in our process was to mark the locations of confirmed pottery sherds on the ground before photographing them by drone. Dr. McClellan had already assembled a team of field walkers before I arrived, and they had flagged platform 1 in anticipation of my visit. It was covered with red flags, my first introduction to the many archaeological sites in the area. After seeing the first platform already tagged, we headed out the next morning to another field with many mounds arranged in plazuela groups. We talked through the challenge, flying low enough to get sharp, detailed images, but not so low that we risked crashing into cornstalks or limestone boulders. We chose a second mound, now labeled Platform 2 in our dataset, and began tagging pottery sherds there, planting red flags and clusters of broken reddish fragments. We began our low-altitude flights, sending the drone on carefully programmed paths just a few meters above the ground. It skimmed the top of the mound just high enough to avoid a crash. This slide here is intended to illustrate why we needed to fly the drone so low. This sequence of images shows the challenge of capturing sherds clearly enough for AI object detection. On the far left, the drone is just 1 meter above the sherd. You can see the close-up above and the full photo below where the sherd appears as a tiny dot on a piece of white paper held down with a few objects to prevent it from being blown away in the drone's downwash. Even at 1 meter, the sherd is very small and slightly fuzzy, but still recognizable, represented by roughly 10,000 pixels. As you move to the right, the drone's altitude increases up to 5 meters, and at that height you can see the entire picnic table in the frame. But the sherd itself is barely visible. It's represented by only about 500 pixels, which is hardly enough for reliable detection. So the takeaway is clear. To get usable images of such small objects, you need to fly as low as possible for image quality while staying high enough to keep your drone safe. Here's what the pottery sherds look like up close, photographed with a handheld iPhone from below waist height. They're made of reddish clay with white sand inclusions. That distinctive red tint is what led us to believe AI might be able to spot and detect them. And here's another handheld photo showing a cluster of sherds, just what you might see if you were walking across the field. And this is a drone photo taken from 3 meters up, 3 meters above the ground. Can you spot the pottery sherd in this image? And now here's the same sherd partially hidden behind a cornstalk. From this height, you can see just how small it appears in the photo. And as you can see, each sherd is represented by just a handful of pixels, roughly about 25 across and 25 down. That's barely enough for basic detection, so we're relying on the distinctive reddish color of the pottery to help the AI recognize them. Without that tint, there simply aren't enough pixels to confidently identify these as sherds. This image was captured by the drone at a height of 3 meters. 2 pottery sherds are highlighted in yellow to illustrate their scale and visibility at that altitude. After we returned to the studio, I prepared the drone imagery for AI model training by converting the raw DNG files into 2 formats, high-quality HSV numerical arrays and TIFFs. I embedded the coordinate reference system in geodata, converting the processed TIFFs into geotiffs, and then I curated a set of non-overlapping photos that covered the target areas. And these geotiffs were used to outline the sherds to make a layer of pottery sherd polygons as a cookie cutter for extracting the sherd pixels from the images to make AI training samples. This Python module extracts individual sherd images, hundreds of them, to be training samples for the AI model. The samples are HSV pixel arrays made from the images. We're using HSV, that's hue, saturation, and value, to focus the deep learning model on the distinctive reddish hue of Maya pottery. This Python module will handle the deep learning model training, ingesting the training samples and essentially small cutouts of pottery fragments, and analyzing their visual patterns. Through digital cogitation, our AI will learn to recognize Maya pottery sherds. That's our goal, and we're nearly there. Then comes the real test. We'll run the model on photos from other agricultural fields it's never seen before. Will it detect sherds at all, and if so, how accurately? We will generate industry-standard test scores to evaluate the model as a proof of concept. I expect our first version will be like the Wright brothers plane, sort of a proof of concept rather than a polished solution. But our innovation is real, using low-altitude drone imagery, processing it as HSV arrays, and applying these tools to enhance the age-old practice of field walking. I'd like to close this presentation with a few insights that presented themselves to my view as I worked on this project. First, we need drones that simultaneously capture both LiDAR and visual light imagery, syncing and combining them into 3D models and making a virtual twin over the terrain as they fly. Second, this kind of imaging needs lots of computational power, and on a small, lightweight drone, that's simply not feasible unless the drone streams its data back in real time to its home base, perhaps to a computer in the back of a pickup truck where the data is received, recorded, and converted into a digital twin. So third, that digital twin can assist with drone navigation, streaming flight instructions back to the drone as it flies, creating two-way streaming media to enhance recording and navigation capabilities. And so fourth, with this enhanced imaging and navigation system, drones could safely operate at extremely low altitudes, helping them maneuver more precisely through complex terrain. And finally, fifth, with the low-altitude flights safe and reliable, we improve the quality of data collection, capturing ultra-high resolution imagery of in-situ artifacts for making better and more accurate objects detection models. So it's not just about flying lower, it's about seeing better. This concludes my presentation, and I'm grateful for this opportunity. I'm grateful for everyone who's contributed ideas and support. If this can be shared, it will have served its purpose. Thank you.